In the second part of the lecture, I will show you how we are able to do neural network design from the dataset and how you're able to tune your configuration model to know whether it is optimal or not and what we should change in the network settings in order to ensure that you're able to obtain high accuracy performance with perhaps low error. So, but before that, there is some common question regarding the neural networks. So the first one is what is a hidden layer? So hidden layer is a layer in between of input and output layer. So it will be responsible in order to memorize the data that you want to map between input and output, and you will utilize the information in order to predict the unknown or an unseen input from the layer. The second thing, how many hidden layers should I use? So hidden layer, the number of hidden layer, you should try to use the simplest or the lowest hidden layer at the time. So most of the time you start with one and then increase that thing to two, three, or four. But you need to remember if you increase hidden layer, so means that you add more complexity to the system, and it will be takes longer time for the network to converge if you have many hidden layers. The third thing, what is hidden node? So hidden node is the neuron inside of the hidden layer. uh, so the same thing is happening. So for each of the hidden node you have the activation function, in which for each of the hidden node you will have the layer of wicks that connect in terms of the input that fed to the neuron. The second thing that is quite important is the problem of the overfittings. So for this case, the cross point here is your training data set. So what is the overfitting, underfitting, and nicely fit? So for this case, the blue line, which is consists of the 5 neurons in hidden, can be considered as the nicely fit solution for these networks. Whereas for the red line, this is one of the problem for underfitting, in which the training dataset unable to fulfill the requirement uh, from the constructed model. And then finally the green line shows one of the problem that we consider as the overfittings. Overfitting means that if you look at of this line, so it able to fulfill 100% of the training data set. However, it will fail in order to predict a new data set, new data that will lies in between of these two point. So in which for this case, if we try to map the data from here to predict the data from this line, so for the red line, it is obvious that the data is under the training data set. The blue line is perhaps the best prediction in between of these 2 points, whereas the green line is overfitting, means that you fulfill the 2 points requirement, but in between of that thing you fail to predict the things. For underfitting, you enable to fulfill in terms of the training data set, and then for the blue line, it can actually fit to the data well. So basically, I will show you later on in much more details from the example how we're able to know whether your training data set and validation data set is overfitting or underfitting based on the plot of the training output. So one of the method that we use is the cross validation. So cross validation basically is a method in which you have the dataset And then the dataset will be divided into training and validation. So depending on the ratio, whether 70% training, 30% validation, or 80% training and 20% validation. So you need to cross-validate between both segment of data. So in which you need to ensure that you're able to gain the high performance in terms of the training dataset, and then at the same time also the same perform the most highest performance for the testing. But most of the time we will look at the testing performance. Your testing performance must be better. If your training performance better, means that your network just able to memorize the data well, but in order to predict whatever in between, it failed to do it. So that's why most of the time we will look at the validation data set in order to configure, or in order to give some conclusion whether your model is good or not. So, but before that, let me show you simple example on how you're able to use the multi-layer perceptron to solve this problem. So for this case, you are given 5 sample of image, in which every image will be labeled as 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0. So the aim is that we want to train our neural networks in order to recognize all these shape, and then later on make a prediction when we give different type uh, of this shape in different perspective, different dimension, different size, different location, and etc. So the problem can be simplified into this configuration. So for this case, we use this type of multi-layer perceptron configuration. We have 7 layers in the input, in which the features will be extracted based on the hue moment. So you can try to Google on what is the hue feature extraction. So we have the 7 node of input layer, and then for the hidden layer we have 1 2 3 4 5 6 7, also 7 node of the hidden layer. And then for the output will be the same based on your configuration. So from our previous case, so we have 5 bits of label tagging. So in this case, we will use 5 labels of output neuron. So for this case, we don't use any bias for hidden and output. So let's try to look this problem, how we're able to solve that thing. So basically, this is our configuration. We have 7 input layer, 7 hidden layer, and 5 output layer. So there is some setting for our model for the learning rate, momentum term, and then sigmoid function. So what we do first is we randomize the weight, and then we train the model. So this is the area of training. So since we just trained for 5 uh, sample images, so it will be quite fast in order to train the models. So let's try to validate the performance of our system. So basically, this is the tagging. You just need to remember the tagging. So let me try with respect to different type of test image. So let's say for the first class of the image, which is the star, so we try to recognize this shape. So in this case, the prediction is 0, 0, 0, which is consistent with our training level. So even though in this case we have some noise surrounding the objects, so the next part we try with respect to the bigger dimension of the star image. So the same, which is correct. So the third thing is we skew the image. So this case is failed to recognize that thing. Next, we put it in different location. So it's quite good, able to recognize the things well. So next we move on to the second object. So for the second object is 0001. So we try that thing. So the prediction is quite low, 0.5, but since we put some threshold, still recognized as 0001. So next we try to use image that is rotated, for that thing to 001. So quite good in terms of the recognize the shape. And then just small one, we test that thing. Okay, so it's okay. So let's move on to the third shape, in which we put the bigger circle shape. So we test that things 10, so almost the same with the label. And then the smaller one, okay, 10. So next, image 4. Image 4 is circle plus cross. So the bigger size of image, and we rotate the things, so the performance is 1. Okay, so it's okay. Next, quite small. Okay, consistent the outcome. And then finally different location. Okay, and then finally the final object. The final object is supposed to be 1000. Okay, so 1000, so it's okay. So we try with different configuration. So it failed for this part, for this object. So next, this object, okay, it's good. And then finally maybe this one, okay, 100. So there is one way how we're able to utilize the model in order to recognize simple type of object. But actually the performance of the system is related to two factors. The first one is based on the features extracted. So since I use the who moment, since who moment is invariant under the rotation scale change, so that's one of the reason that for this case I can just train the sample by using just 5 image, in which only single sample of image for every class. It still looks good even though your sample is limited. However, in a real application, most of the time you need to rely on the high data set. So that's one of the reason we move on to the second part of the problem, in which for this case we will train the image by using the MNIST dataset by using the multi-layer perceptron neural network. This is just we use the simple structure. So first thing first, what is the MNIST dataset? So MNIST means that this is the database that constitute of the handwritten digits from 0 to 9. This is handwritten for 0 to 9. And then there's a lot of the training dataset, 60,000 for training, and 10,000 for validation or testing. So it's quite good. So 60,000 and 10,000. So for the configuration, the input dimension image is 28 times 28 pixels. So this is some example of the MNIST dataset for 0, 2, 4, 3. So it's from 0 to 9. So mean for this case you have 10 neuron in the output layer. So this is the initial configuration that we will try in Python later on. So we have the input layer with the input neuron of the 784. 784 means that 28 times 28 pixels. We just fed directly all the pixels into the input node. And then for the hidden layer, initially we just put 5 to 8. I will show you later on what is the difference when you put different type of numbers for hidden node. Let's say we put small numbers or bigger number, what is the effect? So, and then obviously for the output layer, since we have 0 to 9, so we will have 10 neuron in the output layer. So for the training session, we use epoch 5. Epoch means that the same dataset will be fed to the system 5 times. Batch size is for one training session. For every iteration, you just take 128 samples and then update the weight. So because of this, since you have the 60,000 dataset for the training, so we will have 496 iteration in order to complete the 60,000 dataset training at one time. So for the we will use the Python software in order to do the training. I have do the coding. I have modified the coding a bit with full of the comment in Python. So basically, if you want to try, and then I strongly suggest you to try this example. So you need to use this configuration. You have Python. You need to use the Python 3.6. The minimum requirement. It can be 3.6.10 and etc. So you need to install the TensorFlow by using this command pip install TensorFlow, and then Keras pip install Keras, and then NumPy pip install NumPy. So NumPy, the version will be 1.16.2, and then you need to install another toolbox, which is the Matplotlib. This is the toolbox that we will use for plot the image. So basically I have opened my Anaconda here. So when you open the Anaconda, you will see the screen of the navigator. This is the dashboard. The first thing that will appear when you open the Anaconda. So basically, this is the part where you can set your own environment. So means that if you want to set up one environment in which maybe use different version of the TensorFlow, you need to set up with different version of the NumPy and etc. So you can set your own environment, different environment. So that during runtime, you can just select the environment. For this case, I have a configuration for the GPU, for CPU. So for this example, I have set up the environment which is suitable to run the code that I will provide you later on. So you can try it. So this environment will use configuration that I have listed here. Means that Python 3.6.9, TensorFlow, NumPy with version 1.16.2, everything here. So so once you have opened the Anaconda navigator, so you will see a lot of other subtools you can use. But for this case, I will use the spider. Spider will have almost the same environment like MATLAB, almost the same setting. So you have the command, the command part. You have the M file part, and then everything almost the same. So this is the dashboard for the spider. So I have do some coding here. I have modified the coding actually with the comment and then add some plotting library. So basically, for the spider, the left side of the part is where you do the full coding. The same with the MATLAB. If you want to save the code in M file, so this is almost similar with the M file. So this is the part in which you type the command. It will directly execute the command. Whatever you type here, it will execute the same thing. So the next part that you need to know, you have some tab here, variable explorer, plot and files. So file is where you tag your output will be. So in this case, the default is C user, but I will change the directory to my Python file directory. So when I put that thing, so this is all the file inside the new directory. So this is my working directory. So most of the code is here. So you can see this is the cross MNIST comments. So the code is here. So when I want to save the output, I just put the save command and then it will be saved in this directory in Python. So for the code, so it will take some time in order for you to understand the code, but I have put most of the details comment in each of the code that you will use. So we'll try to explain the things in the simplest way perhaps possible. So for the first part of this thing is, let's say for the command from class.dataset import MNIST. So this is the command in which you import the database to the working environment. So in Python, for the command of the from import and everything, so this is almost similar in C. If you put let's say include stdio.h, include whatever.h. So this is the same thing. You just want to take the configuration from Keras and then put it in your own environment model. So this is the way. So basically for the Keras, we have the models to construct the neural networks, the matplotlib library to plot the output of image. NumPy is to execute some mathematical operation like transpose, reshape, and everything. Layers, I mean this is the layer that you will use in your neural network model. Let's say input layer, hidden layer, output layer. So for first in constructing or designing the neural network, we have three sections that is quite important. The first part is how you pre-processing the data. So in this case, for pre-processing data, the first part is we just download. This is the command in which we download data from the dataset. So for the dataset, the next part is this is the pre-processing part. So for the pre-processing, for this first command, we just need to reshape because of your image in 2D dimension, whereas your input of the neural networks will be in the 1D dimension. So that's one thing that you need to reshape the input image. So the second part of the pre-processing of the data, so we normalize the data. So usually for the neural networks, it is a good practice that instead of you plug in the big value of data, so let's say for pixels you have 0 to 255, you need to normalize that thing to 0 to 1, so that your network will be converged much more faster in comparison you just fed the data in different type of format. Let's say if you have three dimension of data, in which first dimension is 10, second dimension maybe 300, third dimension will be 4000. So if you fed that thing directly to the models, so it will be quite hard for model to estimate that thing. So the best way is for every dimension of the data, you just normalize to from 0 to 1 and then fed that thing, so that it will be easy for your network to learn the model properly, and then discard in terms of the different scale value. So that is the first part. The first part means that how we are able to pre-process the data set. So the second part is how you construct the model. So the model can be constructed by using this simple equation. So this is the almost the same thing for every model that we will use later on. This simple multi-layer perceptron. So the next model, the convolutional neural networks. So we will use the same command, which is we will use the models that sequential. So in Python we have two type of models. The first one is the model that sequential. Second one is the model that functional. But for this class session, as a beginner, we will use the simple model dot sequential for every example. So this is the configuration of our model. So the first part is that we add the layer. So in this case, we add the hidden layer with a number of 512, and then for the hidden layer, the input is taken from input image, which is in the 28 times 28 dimension. And then for this model, we use the activation of the ReLU, rectified linear activation function. So this is our hidden node in which you plug in straight away the input. And then later on, we just have three layers. We have the input, we have the hidden layer, and then we put the output layer. So for this case, we have 10 node for the output layer, and then for the activation, we use the softmax. Softmax activation means that it will give you the probability 0 to 1 for every node or in the output layers when you do the training and testing. So that is the second part. First, you pre-process the input and output data set in terms of the change the shape, normalize the thing. The second part is you construct your models. So you can actually add let's say 3 layers, 4 layers by modify this part. So once you have modified this part, the next part is how you want to configure the model, what is the method. So in that command, we use the network.compile. So network.compile will have 3 parameters. So the first one is the optimizer. Optimizer is what is the method that you want to use in order to update the weight. So let's say from our example, we use the backpropagation. So but for this case, we use the RMS properties. Next, the loss. Loss function for this case, we use the categorical cross entropy. The loss function is same like in our derivation, we use the E equal to half tk minus ok squared. So this is our error function, loss function. So what for this case, we use the categorical cross entropy. And then a matrix. Matrix means that what do you want to measure in terms of the performance. So most of the time we want to measure in terms of the accuracy of the model. So once you have the layer, the setting, you set in terms of how the training parameters should be configured, and then you have everything. So this is the command that will execute or start the training process. So by using the network.fit. So network is actually you obtain the models this thing, they were equal to models dot sequential. So this is the models that we import from the keras. So one thing, the best part of the Pythons, you don't have to declare the variable. So let's say in C, if you want to use the integer, you need to define integer first. Let's say in C or in basic in dim A as integer. But for Python, it is dynamic variable. So you just need to fed that thing, and then Python will configure what type of data that is suitable for this input. So this is the command that will execute the model. So the next part is that what you fed to the training session. We have the training image, training labels. This is the input output tagging, or this is the target, this is the input. Epoch, okay, let's use the same setting that we set here. So in which we have the epoch 5. So batch size 1 to 8. So this is the training dataset, this is the validation dataset or the testing dataset. So we fed the same thing, test image, test label. Okay, so once we do the training, so we will obtain these 4 parameters from the history. So this is only the part that will plot the items, and then it will show you the nice graph that is obtained from the training dataset. So now we will train the system. So if you want to ensure that you're able to plot the item properly, which is the pop-up of the figure, so you need to use this command, which is the matplot library qt5. So we use this setting in order to ensure that the figure will be pop up. If not, the figure will be live inside of the command console. So once we enter that thing, we can run the model. It will take some time for the model to execute the process. So it will show you some what is actually happening for every training session, what is the validation accuracy, the training accuracy. So we just wait until the training session completed for 5 epoch. Okay, so finally we have this output, the plot output. So we have 2 figures. The first figure is the training and validation accuracy. The second one is the training and validation loss. So this training loss should be goes to 0. The accuracy should goes to 100. So for this case, you can see from here we just have 5 epoch, 1, 2, 3, 4, 5. So from this training session, what I can conclude is that your training, as you increase the epoch, we goes to 100%. However, your testing or the validation dataset, so up until for this case is epoch 2, it will retain at set. It will retain at 97. You need to look this part, bottom left part. So you can see at epoch round 2, your accuracy is around 97%. So for this case, after epoch 2, your model start to overfit. Overfit means that your accuracy will be increased in terms of the training. However, the validation will either flat or will either the performance become worse. So that is the thing that you should consider when training. You need to pick up the best approach. That is the first thing, the simplest thing to tune your model. So let's say if I increase in term of the approach, instead of 5, we use the maybe around 15, just to increase the approach to see what is happening for approach of the 10. So this is 15. Okay, we just retrain back everything. Okay, so basically, if you look at the from the command console, so after the 15 approach, your accuracy is around 99% for training, whereas the validation accuracy is around 98%. So we look at the, so usually we just focus on the training and validation accuracy compared to the training and validation loss. So what we can deduce from this thing, almost the same thing happening. So means that your validation performance just capped at 98%. So means that it just going up, going down. So means that let's say after for a push, your accuracy around 98%. This is for a push. After 10%, almost the same thing, which is 98%. So for this case, approach number 4 is just nice in order to ensure that your performance will be quite configured optimally. So for this case, you can change the code to ensure that this thing will be a push of 4. So we just make a quick retrain of that thing with a push of 4, so that we can see the performance of the things when we test with single image, multiple image, and etc. So this is the performance. There will be reduction of the validation accuracy, but it's okay. So for this case, for the training accuracy is around 98, and then validation accuracy is around 97.88, which is around 98. So this is the plot of this figure. So now for this data set, okay, there are many things that you can test later on. So one of the thing is that you can save this thing. Let's say you have trained everything, and then you say this is the optimal networks configuration. So you can save the model by using this command, which is network.save. So if I just put that thing, so let's say so it will be in the .h5 format. uh, let's say tnn try.h5. So if we save the model, so you can see the name is tnn try.h5. So you can see, so there is the, you see, so this is the file of your model. You can load that thing and then you can test the performance. So let's say one thing that if you want to view the image, let's say what is the image that was trained in the testing or training data set. So you can do that thing by using this command if you want to see the data set. So for this command, there are two methods. So this is if you want to take the image before the reshape. You need to remember, before we training the dataset, we have changed from the 2D to 1D. So if you want to see the dataset, let's say if I want to, let's say if you want, I want to view the data from this is test image, maybe image number 7. Sorry, test images. So you can view the shape of the data. So in this case is 7 at 4. So if you want to view the data in the 2D dimension, so we need to reshape the data a bit to ensure that you can plot that thing. So you can use this command, which is plot in .imshow. So for this case, we can reshape the image. So let's say, so we can reshape the image by using the command of mp dot. I have put all the important command here. So you can reshape by using this command np dot resize. So in this case, np dot resize. What do you want to resize? So your input will be based on the view data. Okay, and then the dimension. So our image is in 28 times 28 dimension. So in this case, you have the data reshape in 2D. So let's see if I view. So it is 28. So if in 28 you can see the image in test image 7. So test image 7 is, you can plot the image by using this command plt dot imshow your view data 2D, and then plt dot show. So this is the image from test image number 7. You can view the label here, test image. Okay, this is the test image, this is the test label, so number 7. So number 7 is 1, 2, 3, 4, 5, 6, 7. So number 7 here, the label is actually 9. So the label 9. So this is the image number 9. So if you want to evaluate the model performance or in runtime, if you want to feed the image, so you can use the command which is network.predict. So in this case, network.predict, you can predict the shape of object, single object. So for this case, let's say if you want to predict what is the image here, you just fed the image to the model so that you see what is the expected output. So in this case, you know, right, this is number 9. So if you fed to the model, what is happening? So I use the same data, which is view data. We take the test image from location of 7. So what you need to do is that you can just use this command. Let's say I just take the whole thing to make the thing simple. So this is the command in which you need to resize your test image first before you can actually do the. So in this case, we take test image number 7. So np.resize, this is the thing that you do the transpose of the data, because original data in 7841 dimension. But if you want to fetch to the predict, network.predict, model.predict, so you need to transpose the data so that you're able to get the proper configuration for the input. So so my prediction will be lies in the prediction variable. So this is the prediction variable. So in prediction variable, so you remember that we have the 10 bit of output, so 0 to 9, which is, for this case, number 9 will have the highest probability, whereas the rest in this case will have a lower probability. So you can see all the models here. So if you want to see all the prediction, you can fed all the data set. Let's say I use the predictions with S, means that I just want to test the whole performance of the system instead of the single image. I just put network.predict. You just need to put test images. So test images consists of the 10,000 image. So this is the whole prediction of the 10,000. You can compare that thing side by side with respect to label manually. So predictions with S means that I have the data. This is the 10,000 of the 10-bit output data. So this is the data. So means that starting from number 0 to number 9,999. So you can compare with respect to the. So this is since the prediction. So this is we use the test label. Test label will be same dimension. So this is the label, and you should make sure that your model able to predict the same. So of course with some probability. So in this case, first data 7. So this label is 7. Say data number 4 is 4. So the prediction is 4. So there is the whole things regarding the map of the predicted output. You can compare that thing with the label and etc. So what you can do next is that you can either change the, let's say I change the, you can change the input variable, sorry, the number of neuron in the hidden layer. You can change the activation function, whether instead of the rectify linear, use the sigmod and etc. So there are many things. So hopefully you can try it by yourself, and then later on in our next chapter, which is the advanced part of the multi-layer perceptron neural networks, we will learn about the deep learning, how you able to construct deep learning, and then later on we will learn about the how you can construct your convolutional neural network models by using Python. I will teach you about the basic theory, and then how we can actually construct your own model using Python, do the training, and then validate the training, whether the configuration output or the training was optimally done, and how we can cross validate between the training and testing dataset. So I think that's all. Thank you very much.